Hi everyone. In today's lesson, we're going to learn about the different forms of equations for planes in R3. So let's get started. And we're going to start with a bit of a warm-up. So back in grade 9, you guys learned about equations of lines and even vertical lines. For example, the line x equals 5 in 2 space or R2, that rule x equals 5 says everywhere along this line, the x value is 5. The x coordinate is 5. So it gives you a vertical line with x equals 5. And in R2, each point on the line x equals 5 would have would look like this. It would have an x value of 5, and then y can be anything, and it still would satisfy that rule, x equals 5. So what we want to think about is, well, what would that equation look like, or what would that graph look like for that same rule in R3? What would that graph x equals 3 look like? So if you look at those 3 planes I've given you, and you use this initial discussion we've had about x equals 5, giving you points where the x value is 5, can you figure out what the equation of these 3 planes in R3 would look like? So if you want to pause it and think about that for a second, and unpause when you're ready, you're just kind of figuring out a rule that all the points in those planes obey. And you can, as I said, unpause it when you're ready. I'm going to take them up right now. So if you look at this first example, all these points, and every single point on this plane, the x value is 3. This would actually be, this is the equation of the plane, of this plane, x equals 3. In graph 2, on that plane, all the y values are 3. This plane comes from the equation y equals 3. And in a similar way, the plane illustrated in part 3 is the plane z equals 3. So in R3, these kinds of equations give you a plane. Can you guys do some more complicated ones? So you're given a couple of planes there, and at least 5 points on each one. Can you see a rule for these planes, and then turn that rule into an equation? So let you guys can pause and think about that for a second, and unpause when you're ready. So if you look at the first one, for all those points, there's a relationship between the x and y value. So loosely speaking, the x value equals the y value for all of those, every single point there. So we can turn that into math. This is x equals y, or you could say x minus y equals 0. And that would be the equation of this plane for plane 2. In this case, if you look at all the points, there is another relationship between the x value and the y value. The x value is the negative or opposite, whatever way you want to think about that. The x value and y value are opposite signs. So we could say here that x equals negative y, or x plus y equals 0. And these are just rules that only involve the x and y value. And more involved planes will have rules for all 3 of the coordinates. You guys try these ones. So pause and unpause when you're ready. All right. I maybe should have done these ahead of time. I can see the rule for the second one. What's the rule for the first one? 304, 1, negative 2, 2, 301. Oh, I think I see it. It was a bit hard to see. So the rule for the first one is that if you take the x value and subtract the y value, you get 3. X value subtract y value is 3. And so turning that into math, x minus 3, or x minus y equals 3. Or, you could write it as x minus y minus 3 equals 0. And that checks out. 1 subtract negative 2 is 3. 3 minus 0 is 3. And the z value doesn't really factor in here. And the last one, the rule would be if you look at the x and y values, they add to 4. Plus y value is 4. So the equation for that plane, or a equation, would be x plus y equals 4, or x minus y minus 4 equals 0. So none of those rules had a z component in them, and lots of planes do. We'll see that. But hopefully this warm-up gets you, just used to the idea that, just like a line in R2 is just a graph of all the points that satisfy the equation. The same thing is true with planes in R3. All right, so today we're going to talk about different ways to state the equation of a plane. So what we've been doing here is actually, we just did some examples of determining the scalar equation for several planes. And what you will probably notice today is that various times I slip in between scalar and Cartesian, just because the new resource I use in the old one was scalar, one was Cartesian. And I'm just still used to using kind of both. So I kind of slip into both now. But yeah, all those plane equations we had were kind of in this form. That might look like the equation of a line in R2, and it kind of looks like that, except it has an extra z component. So when we add a z component, we now have a scalar Cartesian equation of a plane in R3. And that brings us to what other forms do equations of planes have in R3? So right now we've done lines in R2 and R3. So we saw that in R2, we have our classic grade 9 slope-intercept in Cartesian or scalar. And then we saw that we can figure out vector and parametric equations for lines in R2. Then we took it to R3, and we saw that only lines in R3 can't have a slope-intercept form and can't have a Cartesian equation. Because in R3, a line doesn't have a slope. You can't say rise over run in 3 dimensions. And there was no unique normal for a line in R3, which meant there was no scalar equation. But there were vector and parametric equations. So the idea of a plane in R3, we're going to take some of the concepts we've used and extend what we've done, like with lines. So here we go. So first, we're going to think about, what things define a plane. Like I know that in R2, in 2 space, what do I need to determine a line? Well, I know if I have 2 points in R2, 2 points make a line. Any 2 points that aren't the same point will make a line. Well, what about in R3? What kind of conditions can make a plane? Well, the first is you have 3 distinct points. So I'm just gonna, and I'm gonna also add here that these 3 points cannot be all collinear. So if you have 3 points, A, B, and C, those 3 points uniquely define a plane. There'd be one plane that goes through all those points. The reason why they can't be collinear is that if they were collinear, then you could just kind of rotate that plane along that line, and you can get lots of planes through all 3 points. But if you have 3 not collinear points, there's going to be one plane that goes through them. Also, if you have a line and a point not on that line, that defines a plane too. So for example, here's a line, call this L, and some P, not on the line. So if on R3 I said here's a line and here's a point not lying on that line, there'd be one unique plane that contains that line and passes through that point P. And there's 2 other cases that involve lines. If you have 2 intersecting lines in R3, there's one unique plane that will contain both. So I'll call that L1, call that L2. And the final case is if you have two parallel lines. And I'll say, I'm just going to add in distinct so that they're not the same line, because we've seen that, the equation of a line can have infinitely different many forms, and they can look rather different. So I'm going to add here that they have to be distinct. They have to be different lines. So if you have two lines that are parallel and not the same line, there's one unique plane that goes through them both. And so we might come across any of these situations and have to find the equation that governs this plane. But these are the four different situations that give rise to finding the equation of a plane. To find the equation of a plane, we have to think about linear combinations of vectors. So if you recall, so any two vectors that aren't collinear are going to span a plane. So what do I mean by that? I'm going to try to draw a big visual here. So I'll call that vector A. Call that vector B. And if I want to get anywhere on this plane, like let's say I want to get to here, right? Well, I just take a scalar multiple of A and add in a scalar multiple of B. So I'll call that SA and T vector B. So I just take a linear combination of those two guys, and that can give you vector R on that plane. And I can get anywhere I want with different values of S and T. So I can write this. Any vector R is just some linear combination, some number times A, vector A, plus some number times vector B. And S and T are real numbers. So that's a big idea for how to find the equation of a plane. So guys, remember with a line, whether it's an R2 or R3, for a line, if you want to specify its direction, you just need one kind of direction vector, right? With a plane, it's different. With a plane, if you want to describe all the points in the plane, you actually have to give two direction vectors in order to get all the points in the plane. That's kind of the big idea for today, is that to get the equation of a line, you need a point in one direction vector. For a plane, you need a point in two direction vectors, because it's two vectors that span a plane. One vector spans a line. So we're going to develop the equation, the vector and parametric equations of a plane. On my graph here, I'm going to draw a point here, and I'm going to call it P sub 0. And I'm going to draw a vector that goes to that point, and I'm going to call that R sub 0. So that vector R gets us to this plane. From there, if I want to describe all the points on the plane, well, now I'm on the plane by going to this point P naught. And to describe all the other points on the plane, I need my two direction vectors. And we're going to call them A and B. We could have called them M1 and M2 for two different direction vectors, but then that just gets hard with the labeling. So we'll use A and B for this one. And the idea is that, and I'm going to kind of draw what I had on the previous one, is that I can describe, I can get to any point anywhere on this plane by first getting to the plane and going to this point P naught, and then taking a linear combination of those two vectors, S times A and then T times vector B. So here's that big idea. The vector equation of the plane looks like this. And I should note too, you can see that if you're wondering why I have the pi symbol after that, well, to label our lines, we usually use the letter L. To label planes, using P is not very practical because we often use capital P for points. So we might refer to our planes with a pi. And I'll often use a capital pi, which is just like a straight line on top to denote planes. But the vector equation of a plane looks like this. R equals R naught plus S times vector A plus T times vector B. And here S and T are just real numbers. So this actually looks a lot like the vector equation of a line. you have some point on the plane. And instead of having one direction vector, because it's a plane, to span a plane, you need two direction vectors. So here, R naught is some vector x naught, y naught, z naught, which corresponds to a point on the plane. And we'll say A equals A1, A2, A3. And B equals B1, B2, B3. So they all have an X, Y, and Z coordinate. And we'll call those, just loosely speaking, it's okay. We'll call them direction vectors because they kind of give you the idea of where your plane goes. So just take a moment for that to sink in. This is literally just the same definition for the vector equation of a line. You need a point on the plane, and then with a line, you need a point on the line and a direction vector. With a plane, you need a point on the plane, and then two direction vectors, again, because two vectors span a plane. So planes can have a vector equation, and planes can also have parametric equations, where we just break down the vector equation into components. So here, doing that, we would get x equals x naught plus s times a1 plus t times b1. And then do the same thing for y and z. sa2 plus tb2, and z equals z naught plus sa3 plus tb3. And those different values of s and t give you all the different points that are on the plane. So let's continue. So a couple notes on this. Actually, there's just going to be two. I don't think I'm going to use this third one. So the first is that these equations are not unique. So just like with the vector equation of a line and parametric, there's infinitely many points on the line and infinitely many different possible direction vectors. So that meant our vector and parametric equations for lines were not unique. Well, it's even more so for planes because you have infinitely many points on a plane, and there's infinitely many different direction vectors that aren't collinear that could span the plane. And so these equations are not unique. And I'll also say different values for s and t. For s and t generate all points on the plane. And every single point will have a specific value for s and a specific value for t. So let's try an example. So let's find the vector and parametric. So I should be careful here. I should say determine a vector equation and parametric equations for the plane that contains the points, these 3 points. So we know that 3 points are going to make a plane. So what is that? What is that equation? What is a vector equation? So remember, we need 3 things, right? We need a point on the plane, and we need 2 direction vectors. So, it might make sense for us to choose, I don't know, why don't we mix things up? Let's choose, I'm going to keep things simple for my next part of this question. I'm actually just going to choose A. So how about our point on the plane, our R naught? Let's just use A, -1, 2, 5. Well, now I need 2 direction vectors that are contained in the plane. Well, that's easy to get because I know that A, B, and C are all in the plane. So I know the vector AB, the vector AB is in the plane. That can be my first direction vector. And finding that vector is easy. We just subtract the components. So 4 minus 5 is -1. I'm going to assume we've done a lot of these, and we got a big day. We're doing a lot today. So I think I'll just do this calculation. 3 minus 2 is 1. And 2 minus -1 is +3. So that's one direction vector. A second direction vector could be AC or BC. I'm going to use, what should I use for this one? I'm going to use AC. That'll be my second direction vector. 5, I think Yeah, if you were screaming at the video that I made a mistake, I think I just flip-flopped all my X, Y's, and Z's around. I'm sure glad I caught that right away. Yeah, because it's for AB, it's 2 subtract -1 is 3. 3 subtract 2 is 1. 4 subtract 5 is -1. That's better. So for AC, we have 5 subtract -1 is 6. -2 subtract 2 is -4. And 2 subtract 5 is -3. So let's use those guys. Well, now we have a vector equation. R equals -1, 2, 5 gets us to the plane. And then S times 3, 1, -1 plus T, 6, -4, -3. And that's where I'll leave it. I think we understand that S and T are real numbers that give you all the points in the plane. And maybe you're wondering why use S and T for your parameters. It literally doesn't matter. We'll just use S and T. Given that vector equation, and again, that's not unique. I could have chosen B or C for this initial point, and I could have used different combinations for these direction vectors. But using this vector equation, the parametric equations for this guy would be -1 plus 3s plus 6t. Y is 2 plus s minus 4t. And z equals 5 minus s minus 3t. So we have our first example, finding vector and parametric equations. And it's not too bad. You just need to get a point on the plane and find some way to get 2 direction vectors. Now that we found the equation of our plane, we can see if a point's in the plane. So points in the plane if it kind of satisfies the equation. So how do we do that with our parametric equations? And that's what we're going to use in this one. So I'm just going to keep flipping back and forth here. So if our point 151 is on the plane, that means there'll be some specific value for s and t that for each of these equations will give me 1 for x, 5 for y, and 1 for z. So we're going to see if we get an s and t. We're going to find s and t such that we get 1, 5, and 1 on the left side of our parametric equations. So -1 plus 3s plus 6t. 5 equals 2 plus s minus 4t. And z is 5 minus s minus 3t. I'll call those equations 1, 2, and 3. Now, this is a bit different than with lines. With lines, we had one parameter, so we kind of solved each equation and saw if we get the same parameter. So here we have to use our linear system skills. So I'm going to clean each of these up a little bit by just grouping the constants on one side. So for 1, I get 3s plus 6t, then moving the -1 over equals 2. And I'll have s minus 4t equals 5 minus 2 is 3. And then I'm going to move actually the s and t to the left here and get s plus 3t, and then 5 minus 1 is 4. What we're going to do here is we're going to pick 2 of those equations and solve the linear system. Then we're going to see if those values for s and t match up with the one we didn't use. So I'm actually going to solve these 2 guys because I can see that I have 2 s's, so elimination is going to be really easy here. So let's do equation 2 minus equation 3. We get s minus s is 0, -4 minus 3 is -7t, and 3 minus 4 is -1. So we get t is 1/7. What does that give me for s? So I might use the second equation, sub in equation 2. Whatever s is, minus 4 times 1/7 equals 3. So s was equal to 3 plus 4 over 7. So 21 over 7 plus 4 over 7, it's 25 over 7. So the idea is, do these values, so I know that t equals 1 over 7, and s equals 25 over 7. I solved equation 2 and 3, remember. That means that, if you plug those values for s and t in to your second and third equations, you're going to get 5 for the y value and 1 for the z value. But the question is, does it give you 1 for the x value, or is some other point 5, 1 with an x, y, and z values of 5 and 1 on the plane? Let's find out. Let's sub these in the one we didn't use. Let's sub these into 1. Now, if I had solved the system of 1 and 2, I would be checking these in 3. Or if I solved 1 and 3, I would check them in 2. So let's see if it works in the other one. So does 3 times 25 over 7 plus 6 times 1 over 7 equal 2? I can clearly see it doesn't. So I'm going to get 75 over 7 plus 6 over 7. 81 over 7 does not equal 2. So this is not true. So what we have shown is that 151 is not on the plane. I guess what we showed is that, did we show what point is actually on the plane? No, did we? No, to find out what actual point would be, I would do -1 plus 3s plus 6t and plug in our values for s and t. So I'll just leave it there, actually. I was going to do something else, but we've done what we needed to do. 1,5, -1, or 151 is not on the plane. So that's how we can check if a point's on a plane, given the parametric equations. That was a bit of work. So it'd be nice if we had another form to do questions like this. And that's what we're going to start right now. Just like that lines in R2 had a normal and hence a scalar or Cartesian equation, planes in R3 have normals, and so they have Cartesian or scalar equations. So I'm going to do my best here to draw a nice diagram for you guys. So let's say we have some plane in R3. And a plane in R3 is going to have a specific normal. So I'm going to draw, I'm going to draw a normal from, that's not too bad actually. Yeah, it's pretty good. So let's say I have a plane and some normal to the plane. So remember, normal is a vector that is perpendicular to the plane. In the case of the plane, you can have lots of different normals, but with the plane, they're all going to be perpendicular. Like think of your pen pointing out of your desk. You guys can't see that, but any vector perpendicular to your desk that you're working on is going to be parallel. So any normal we have is going to be pointing in the same direction. So I'm going to call this n. And so we've got a plane. We have some normal, call it ABC. And I'm going to call, let's say we have some point on the plane. Call it P naught. So I'm going to show you guys how we can derive an equation for the plane. We're going to let P be some point on the plane. So point P with components x, y, z is just some other point on the plane. Then I hope you guys would agree the vector P naught P is a vector contained in the plane. So this vector that goes from P naught to P, I wrote that wrong. So P naught P is in the plane. So P is a point we know, and P is just some general point. The vector that goes from P naught to P is perpendicular to the normal, right? The normal is perpendicular to the plane. If that vector is in the plane, then the normal and that vector will be perpendicular, which means their dot product is going to be 0. And check this out. So P naught has coordinates x naught, y naught, z naught. So P naught P will have components x minus x naught. Remember to subtract the components. And z minus z naught. We're dotting that with our normal ABC. That has to be 0. So what we get is we get ax minus ax naught, just multiplying these guys out, doing the dot product, plus by minus b times y naught plus cy minus c times z naught equals 0. And rearranging this, I get this. I get ax plus by plus cz. That should definitely be a z up here. Excuse me. Plus some other stuff. I'm going to say minus, I'm going to say this. I'm going to say plus, and we have minus ax naught minus by naught minus cz naught equals 0. If I just let this ax naught minus by naught minus cz naught, I'm just going to let that be its own constant d. Then we get this. We get ax, this new equation for a plane. Ax plus by plus cz plus some number d. Remember, a, b, c is just the normal, and x naught, y naught, z naught just a point in the plane. So all those, that combination of multiplications and subtractions just gives you a number, and we're just going to call that number d. So this should look familiar. This is actually looks like the scalar or Cartesian equation of a line in R2, but this time it's just got a z value. So this is the big idea. The Cartesian equation of a plane in R3 is of the form ax plus by plus cz plus d equals 0. And in this case, just like in R2, the vector a, b, c is a normal to the plane. So that's pretty cool that there's this natural extension from Cartesian equation of a line to the Cartesian equation of a plane. So this is the third different equation of a plane, and it's often a lot easier to work with in terms of determining if a point is on the plane, among some other things. So we're going to do a few examples getting used to that. So here's a first example. So let's say we have a point on the plane, and our plane has a normal of -1, 2, 6. And I guess I should follow my own advice and use square brackets since that's a vector. Point P is a point, round brackets, vector, square brackets. So what's the Cartesian equation of this plane? Well, our first method is to use substitution. So right away we know, if we know the normal, this is great. We know that the equation of our plane looks like this. It looks like -x plus 2y plus 6z plus some number d equals 0. So if you have the normal, you know 3 of those 4 coefficients, and that's great. To get the last one, just like we did with R2, one method to do that is if you have a point, plug in your point. So we're going to plug in the point 2, 3, 5. So -2 plus 2 times 3 plus 6 times 5 plus d equals 0. -2 plus 6 plus 30 plus d equals 0. So that's going to give us 34, and we move it over, we're going to get d is -34. And so the equation of our plane, the Cartesian equation, is this: -x plus 2y plus 6z minus 34 equals 0. If you prefer, if you like to keep your x value positive, you could do x minus 2y minus 6z plus 34 equals 0. And they're both the same thing. They're both the same equation. So yeah, finding the equation of a plane is, if you have the normal, it's really easy. It's great. We could also find the same equation by using the dot product. So if we let x, y, z be any point on the plane, then we know the vector between this general point and point P, that vector will be contained in the plane too. And so the vector x minus 2, y minus 3, square brackets here, and z minus 5, dotted with the normal, will be 0. We know that for a fact, right? Because this vector we've created here is for sure in the plane. Dot with the normal has to give me 0. And check this out. When you apply the dot product, you get the following. You get -x. -1 times -2 is +2. And you'll have plus 2y, and then -6. And you'll have plus 6z, and then -30. equals 0. And when you clean this up, 2 minus 6 minus 30, I mean, we already did that earlier. You get the exact same equation falling out. So you get the exact same equation. It's just going at it a bit different way. And this idea of the dot product being 0 because they're perpendicular, this is going to be useful still in other applications we're going to look at. And I think it's a pretty slick way of finding the equation for the plane. So given a point and a normal, you guys now know how to find the Cartesian equation of a plane. Let's do another one. So how can we find the Cartesian of the equation of a plane through these points? So we know already how to find the vector and parametric equations in situations like these. But how do we find the Cartesian equation? So remember, to do our last example, what did we have? We had a point and a normal. How can we find a normal to this plane? Well, we have a tool to remember the normal is perpendicular to the plane, right? And we have tools to create perpendicular vectors. We have a tool. If you recall, that tool was the cross product. If we could get two vectors in the plane and take their cross product, we're going to have a normal, right? I think I can draw, I think I can fit a tiny visual in here showing that. So let's say I have let's say I find AB and AC. Those are in my plane. If I take their cross product, I'm going to get a vector perpendicular. I'll have a normal, and then I'll be all set. So let's do that. Let's find vector AB. So vector AB is, be careful this time, -5, -1, and 6. And vector, we're going to use AC, just because. AC would be -7, -4, and -5. Well, that's a lot of negatives. So, but a normal for us is going to be the cross product between those. So -1, 6, -5, -1, and -4, -5, -7, -4. So let's do that. So I have to be careful with negatives here. So that's 5, take away -24, so 29. -42, subtract 25, -67, and 20 subtract 7, 13. So I think that's it. So the equation of our plane is going to look like this: 29x minus 67y plus 13z, and we just don't know what d is. To get d, we can plug in a point. So here we're just using the substitution method. I think b looks nice to put in, so I'm going to put in b. So 29 times -1. The y's will go away because it's 0. Plus 13 times 8 plus d equals 0. -29. 13 times 8 is 104 plus d equals 0. So that's 75. D is equal to -75. And so our equation, Cartesian equation, plus, oh, excuse me, that should be -75. All right, we've got it. I might actually just check my answer. It shouldn't matter what points I sub in, whether A, B, or C. I should get the same D value of -75. So I'm actually just going to, for fun, I'm going to plug in A and see if I did it right. So 29 times 4 minus 67 times 1 plus 13 times 2 plus D equals 0. 29 times 4 is 116. Minus 67 plus 26 plus D equals 0. So does that give me 75? 116 plus 26. Hope it does. Minus 67. Yeah, it does. I get D equals -75. So I just checked. I did do it right. And that is the Cartesian equation of our plane. And yeah, this is going to be really useful for us. Later on, we're going to be finding intersections of planes, and having the plane in Cartesian form will be really helpful because we're going to be applying our linear system skills. So that's kind of nice and familiar to us. Vector and parametric equations have their uses too, for sure. But the Cartesian equation is useful for a lot of things as well. So you can hear my kids. I'm sure my wife will notice the door is open in a second. Okay, we've done a lot today. We're gonna do one last example. So, if I asked you guys to go from the vector, say I asked you guys to go from the vector equation to Cartesian equation. Well, you guys now know how to do it because you have a point on the plane, and given two direction vectors, you could find their cross product to get a normal. So you guys are fully equipped to go from, if I added this question and said, determine vector, parametric, and a Cartesian equation, you could do it. Cross product the direction vectors and do what we just did. But how can we go backwards? How can you take the Cartesian equation and find vector and parametric equations? That can be a little intimidating. You might not see where to start. In this case, it's actually a pretty cool solution. We're just going to actually create some very convenient parametric equations to start. So I'm actually going to give you guys two of our parametric equations right away. I'm going to show you guys how to do this. We're going to let x equal s, and we're going to let y equal to t. Why do we do that? Well, x equals s long form kind of makes it look like this. Another way to write that is x equals 0 plus 1 times s plus 0 times t. And a long way of writing y equals t is y equals 0 plus 0 times s plus 1 times t. And what this does is, because to get your we have infinitely many choices for the point on the plane. And what this locks in is that it's locking in saying we're looking for the point on the plane that has its x value of 0 and its y value of 0. And we're looking for one direction vector that has an x component of 1 and a y component of 0. And our second direction vector has an x component of 0 and a y component of 1. So we're just choosing really easy point, direction vector 1, direction vector 2, and then all we have to do is find the last part of each of those things. And that's easiest to do because if we sub in our equation, we can get a parametric equation for z. So we have 4s plus 2t minus z plus 1 equals 0. And I can rearrange that for z just by moving z to the right. Again, z equals, I'll write it this way, 1 plus 4s plus 2t. And now we're done, guys. So I might actually rewrite just off to the side here. I'm going to rewrite our parametric equations. So we had x equals s. How should I write? I'm going to write this as, I'll just write it x equals s, y equals t, and z equals 1 plus 4s plus 2t. Those are possible vector or parametric equations for a plane. Remember though, this s, another way to write that is just 0 plus 1s plus 0t. And t is like 0 plus 0s plus 1t. So check it out. A point on our plane is the point 0, 0, 1. One possible direction vector is 1, 0, 4. And another possible direction vector is 0, 1, 2. And so now we have a vector equation, possible one, r equals 0, 0, 1 plus s times 1, 0, 4 plus t times 0, 1, 2. And it's a very slick way to go from Cartesian equation to grabbing of some parametric and vector equations. That wasn't our only choice. Maybe if the x was by itself, maybe it would have been convenient to say that y was s and z was t, or the same thing if y was by itself. But here it made it really easy to isolate s. All right, as you can see, it's getting a little rowdy in my house. So I'm going to end this video now. Here's some next steps for you guys, some practice. I posted on Brightspace. Stay well, have a great day, and we'll see you soon.